Okay, so the next section we're going to do is about linear differential equations. If you forgot what linear meant, which is I had a test on it kind of, that means that all coefficients are in terms of x. And then also we have the requirement that y, which we're considering the dependent variable, y and all its derivatives are to the first power. Which means that the general equation for a linear differential equation is coefficient in terms of x times nth derivative, and then we just use the same subscripts. As we decrease the derivatives by 1, the subscript notation decreases by 1 until we get down to near the end. So nth derivative, n minus first derivative, etc., etc., first order derivative. And then if it's zero order derivative, then we just say it's y. And this equals g of x. Okay, so this is what a linear differential equation is going to look like. When n is 1, then all we're looking at is this. Okay, so we're going to start with some easier first order equations. So let me rewrite that. Actually, let me skip a step. If we take the stuff that's in the orange box here and we divide by the lead coefficient, a1 of x, then we get the standard form, which is dy dx plus, and then I'm going to have a sub 0 of x divided by a sub 1 of x. I'm going to recall that, or call that something else. We'll call it p of x. And then this g of x, when I divide that by the lead coefficient, I'll give it a new name and call it f of x. So if you forgot what these represent, p of x is a naught over a1, and then f of x was g of x over a1. Okay, so this is the standard form. This is what we're going to be interested in this section. We want to figure out a solution to this equation. Okay, so some assumptions are that we're going to look for a solution where it's valid over an interval, where p of x and f of x are continuous, and we're going to work with the assumption that a solution actually exists. Okay? Now, if we take this equation, so one of the themes that you'll see is that we're going to take what seemingly looks like a new equation and try to transform it into something that we've already seen before, because we know how to work it. I'm going to write this in differential form. So if I multiply through by dx, so in differential form, we get dy plus p of x y dx, which equals f of x dx. So then, if I group the dx terms together, I'll factor out p of xy minus f of x. So then I have 0 on the other side. And now, what we're going to try to do is make this into an exact equation, like the ones that we did in the previous section. Okay, so what we're going to do is try to find, so the goal at this point is to find mu of x so that when I multiply through by mu of x, mu of x dy plus mu of x times p of xy minus f of x dx equals 0 is exact. So that's the goal. And by the way, I'm going to call this later. I'm going to refer back to this. I'm going to call this star 1. Okay. Now, we know that the differential equation is exact when what?
When partial n partial y is equal to partial n partial x.
Right. Now, what is partial m here? Usually it's m dx, right? And n dy. So this is our m. So we want to write partial, what, y? Of this thing. So p of x, and you know what? I dropped my mu. Let me rewrite that. Sorry. So we want to take partial derivative with respect to y of the coefficient of dx. And we want to make sure that that equals the partial derivative with respect to x of mu of x. Okay, so in other words, partial y of m and partial x of the n coefficient need to be the same. If that's the case, I'm going to kind of rewrite this, put this on the first side. We have a partial derivative, but this function is in terms of just x. So what I'm actually going to do is write it as an ordinary derivative, because it would be the same. So I'm going to call it d mu dx, because that's what this will be. And then if I take the derivative with respect to y of this, the second term here is going to cancel out. And then the derivative with respect to y of this first term will just be the coefficient of it. Does that make sense?
No.
If I were to distribute mu, I get mu times p times y minus mu times f.
Okay.
Partial y, the second term would have no y's at all, so that doesn't mean anything. And then since this is just y to the first, the derivative with respect to y of this will be mu and p. Does that make sense? So I'm going to say that d mu dx is going to equal mu of x times p of x. Which is now something that we can figure out. It's separable. If I separate, I get d mu over, and I'm going to just write it as mu. D mu over mu equals p of x dx. If I integrate both sides, we get that natural log of mu is equal to the integral of whatever p of x is, dx. And if our goal was to actually figure out what mu of x was, remember that's what we wanted to figure out is what mu of x is, well, I can do that here. I just exponentiate both sides, right? So we get mu of x is going to equal e to the integral of p of x dx. I don't need a constant here. I mean, there should be one here, which you could rewrite in front of the coefficient here, but the constant will actually come in later anyway. So when you're finding an integrating factor, really this is all you need to remember right here. Okay? So now what was the point? The point is that when we multiply, so if we go back, if we actually found the integrating factor, we've turned this into an exact equation now, right? Which then means, so let's, from star 1, I'm just multiplying everything now. Let's see if I can pull it up. So I'm going to, yes, question? Oh, okay. I'm going to take the equation here, multiply by the integrating factor, or in other words, just replace mu of x with this formula here, e to the integral of p of x dx. So now I have e to the integral of p of x dx dy plus, e to the integral of p of x dx. And I'm going to kind of move some stuff back around. So back up here, I'm going to put the function f of x back on the other side. So that now it's going to be e to the integral of p of x dx p of x. And then we should have a y in there still. And then this has the dx. And now on the right-hand side, we're going to have e to the integral of p of x dx times f of x dx. The whole point of this was that now this left-hand side represents the derivative of the product of the integrating factor and y. If you don't see it, think about it for a second. To do the product rule here, first you'd have to, let's go with respect to y first, so then we'd have dy, right? And then we keep the stuff that's in terms of x, so that's this coefficient here. And then product rule says then you do plus derivative of the other function. Well, when you take the derivative of e to something, you get e to something, right? And then you have to do the chain rule. Well, the derivative of the integral will become p, right? And then you still have the y from before and the dx. You guys see that? Okay, so product rule is good here because now we can integrate. Now we can integrate both sides. Okay, so here's a recap of the procedure that you're going to take. First, write the equation in standard form. So it needs to be dy dx with no lead coefficient other than 1 plus p of x y equals f of x. 2. Find integrating factor. 3. Multiply both, big important thing here, multiply both sides by mu. 4. Recognize now that the left-hand side is the derivative of the product of the integrating factor and y. In other words, e to the integral p of x dx and y prime. So the left-hand side will always turn into this. We made it that way. Okay? If you don't believe it, you're welcome to verify that it is indeed what you end up with. Okay? Last step is to integrate. Okay, so that's the procedure we're going to take. Let's do an example. So I have this example here. That one with a twist is optional. Okay, so I have two problems that I want to cover. I think I should be able to get through them. Everybody have these steps down? Okay. So let's suppose we have x times dy dx minus y equals x to the 4. We know this is a linear differential equation, first order, because all the coefficients are in terms of x or constants. So here the coefficient is x, here the coefficient is -1, that's okay. And then on the right-hand side, we're able to have a function in terms of x, or a constant. Okay? So, first, let's write this in standard form. What do I do? Divide by x. So, we get dy dx minus 1 over x times y equals x cubed. That's step 1. So I'll just write them down like we did earlier. Step 2 is to find mu of x. Well, mu of x, the formula was to do e to the integral of p of x dx. Well, what's p of x in this? Yes, so we have e to the integral of minus 1 over x dx, which becomes e to the minus natural log of x, which is really the same thing. If I put the little coefficient here, put it into the exponent of x, does that make sense? It's really just, so I'm going to cross this out and put it here, 1 over x.
Okay.
So this is the integrating factor. Step 3. You're going to take 1 over x, multiply the equation by 1 over x. So now we have 1 over x times dy dx minus 1 over x squared times y equals x squared. I stress at this point to make sure that you actually do multiply the whole equation by the integrating factor, not just the left side. I have seen a few times where students just leave this as x cubed, and it shouldn't be, because you have to multiply the whole thing. Okay? Anyway, on the left-hand side, we can write this now as the derivative of what two functions? Mu, which is 1 over x, and y. And on the other side, we have x squared. If we integrate a derivative, we get 1 over x times y. If we integrate the right-hand side, we get 1/3 x cubed plus a constant. And certainly here we could easily get the explicit solution. We can multiply by x, so we have 1/3 x to the 4 plus cx. Again, if you're a non-believer, if you don't believe that this is this easy, take the left-hand side, do the product rule, and confirm that it is the same exact equation. Okay?
Wait.
Yes?
So from going from 4 to 5,
Yep.
is leave the left hand side alone?
Well, what we're doing is essentially integrating both sides. Yes. Because if we have the derivative, when you integrate, you're just going to get the function that's on the inside, and on the other side, you just integrate with respect to x.
But the mu is usually going to be done to do with like
Well, even if they're not that easy, I mean, at this point, it's kind of nice that you don't have to worry about the left side. It's what's going to happen on the right side that you have to be concerned with. So sometimes it'll be nice, sometimes it won't.
So the left side will always be the
Product,
the derivative.
the derivative of the product of mu and y. Yes. by design. We created mu so that it would work out that way every time. Okay? You guys do see that, right? If you do product rule with 1 over x and y, derivative of 1 over x is minus 1 over x squared. And then you have the y. And then the derivative of y is going to be dy dx, 1 over x. Okay? All right. Why don't you guys try this one? Cosine x times y prime plus sine x times y equals 5x. There's a piecewise example that I thought was pretty neat, but we're probably not going to have time for it. But I can tell you, I think you may have one piecewise problem in the homework. You essentially just have to do 2 problems in one. That's really the trick.
Integral What is the... What is it? What is it? What is it? Simple? Which one is simple?
The integral of tangent? Are you having trouble with that one?
Are you having trouble? All right.
Why?
If you write tangent as sine of x over cosine x, then you have minus du in the numerator.
Okay.
So if it's 1 over u, right?
So negative natural log?
Negative natural log cosine x. Yeah.
That's so weird.
The first one is simpler than that.
You're looking at the